last of all, tonight we have another tutor of ours, Jim, come to talk to us about making Sudoku boring with Wavefunction Collapse.
Hi, Doug. I just want to say, like, it's real tough act to follow everybody tonight because everybody's been really good. So I'm going to try and talk about the kind of dystopian future of which is automation of puzzles. So let me. How did I end up talking about? Do you mind just holding with me while I check my screen share works just fine?
Absolutely.
How did I end up talking about quantum physics, quantum mechanics, and yeah, you can see me, and Sudoku. Okay, well, I spent last weekend watching infotainment on YouTube as usual, having a look at level generation for video games using procedural mechanics, and I saw what was people putting an implementation of Wavefunction Collapse to create procedurally generated levels. Like, normally to do something like this, it would probably take at least 3 functions. This first function here would like work to the parameters that we're designing some kind of cityscape, and the second one that we're making an organic pattern, and the third one that we're making like a dungeon type map. But these are all made with the same function, which is, and I'm going to go to, I didn't create this this function, and I will see if I can get some links out into YouTube as soon as possible. But this has been created by whomever this is here, and it's all using one function. It takes a small like bitmap image and generates like huge, vastly different data based on it. And I watched this happen just like this, and it blew my mind, and I felt like I really needed to understand what was going on here. So it uses this notion of wavefunction collapse. What it actually does is it takes an input image, like the sample you'll see here in a second, like that, and then it breaks it up into loads of smaller tile sections, and each of those tile sections it checks against its adjacents, like tiles that are adjacent to it, and it creates a huge stack of potential existing tiles. And from there, once it's monitored all of the like potential adjacencies, it kind of builds it up, and then the output starts off as being all of those possibilities in a giant stack. The function's then going to just pick one of those at random and then turn it into reality. And then from there, it'll propagate the information that something is, something's like being observed, something is that, and it'll propagate all the adjacency kind of issues and produces these huge things. Now, I couldn't replicate this because, you know, I'm not there yet. And the video that inspired me is actually here, and like I said, I'll post these links. So what I thought was, how could I explore this notion in something that's maybe a little bit more relatable? So I thought Sudoku, right? Fairly understandable logic. Every row, grid, and column needs to have possibilities 1 through 9. And you can only have one of each instance in those areas. So you could say that this blank Sudoku here, each of the cells has a superposition of simultaneously all being, it's entirely possible that they're all the numbers 1 through 9. So what happens then if we collapse them? So I wrote a program that's going to do that for us. I can show it off today. So, yep, this seems fine. So what this is going to do is it's going to generate a standard 9x9 grid, fill all of the possibilities with the possibility being 1 through 9, and then it's going to take the one with the lowest entropy. And by entropy, it means the one with the fewest possibilities. And it's going to observe it like you would do, so pre-observed, it's kind of like a Schrodinger's cat situation. It could be anything or it could be nothing. But as soon as we observe it, we have information that you can derive and pass out. So what happens here is it picks a number and then it updates all the possibilities, and we can see this happening, and I put in nice colors. So it then picks the one with the next lowest entropy, and all of that populates out, and you get this really interesting image of the Sudoku working itself out. I could make this faster. I probably should. It is what it is for now. And you can see it's gonna fill itself out and propagate all of that information to all of the connected cells. As each one is observed, it populates that information out to other areas and so on and so forth until we get a completed Sudoku. So then I thought, what happens if I give it information? What happens if I take this possibility space and I populate some of it? So I went onto the internet and I found some Sudokus, and I started with an easy one. Let me just quickly speed up this GUI a little bit. So what happens if we give it a pattern? And this is a standard Sudoku. It was taken off the internet. It was an easy one from, I believe, The Guardian. All the cells are pre-populated, split by new lines, and it's going to show us. And I thought, like, how many so incidentally, 40 decisions it took to make this. 40 decisions it took. So how many would it take to solve this Sudoku? How many guesses would the machine make? So we can see it. First thing it's going to do is it's going to populate all the information and derive all the possibilities from that. Right? We can see that happening. We can see that the green sections are already, some green things are already worked out. I was shocked because it just solved it. Done. There are no possibilities. So then I went for a more difficult option, and it broke. And that's when I spent my entire weekend learning how people actually solve Sudokus, so that I could apply it to this weird solver using quantum mechanics. If there are any quantum, I'm going to go with mechanists. If there are any quantum mechanists in the audience, I apologize if I'm butchering this theory. But I went all the way up and I got to a super fiendish one. And what's interesting is, if you remember the first pattern, it went really green really quickly. So it could work out a lot of things just by reducing the possibilities. I had to put in all sorts of different logic to say how to derive that information further. The more complex it gets, the more not decisions it has to make, because all of this information is still derived, but the more time it takes to work out the next decision. So here we have much fewer stuff derived initially, and then as it fills that out, but it's still so quick. Everything's done. Now we're just waiting it to fill in the blanks. So what I will say is, I'm not a Sudoku genius. I haven't programmed this entirely. It doesn't work exactly. It's still, there are still things that it needs to do that I need to teach it before it, I say teach it, I need to program an algorithm. I'm not using AI or anything like that. Things I need to program before it will solve much more complex problems. I've actually got note of one, save that, where it still needs to make a decision. Save, and let me just open up in this, where's the code where when I make a decision. So it's going to collapse the next wave here. It's going to find this here. This is where we find out the decisions. So I'm going to pause it and save this so that we can see when it makes a decision. We can stop it, and I can show you the derived information that we could do that I haven't yet programmed. So it's still working some stuff out. We've still got some information coming in here, and it's getting a lot of the work. Now, if I let it make a decision, it's going to pick the spaces with the least entropy. So it's going to pick at random something up here or down here where there are only 2 decisions to be made, right? But having spent far too long this week researching how to actually solve Sudokus, the decision to be made is in these 3 cells here. It's not a decision. The information that can be derived is in here. These 3 cells. This one contains the possibility of it being 3, 6, and 9, this one 3, 6, and 8, and this 1, 3, and 5. These 3 cells are the only ones in this area that contain the information 3, 6, and 8. So it's what's called a hidden triple. So this information can only be in one of these 3 cells, which we can then infer this cell cannot have 5 or 1 in it. And if it can't have 5 or 1 in it, then this cell is the only one in this grid that can have 5, and therefore we solve the problem. If I leave it without making the decision, let it decide on its own, it could still come to the same conclusion. So let's find out. Or it could make an entirely wrong decision. I was going to spend some time working on like a backtracking algorithm, but I kind of like the idea that if it makes a decision and it's wrong, we get to find out. So it's got all the derived information. It's going to fill that in first, and then it's going to pick at random. Oh, didn't save. My bad. Oh, please bear with me. Technical issues. All right, so giving the numbers, they must be like these have to be either 8 or 9. So and these have to be 2 or 3. So there's every chance that it could make the right decision here, but we'll just not find out until it actually works it out. Nope, there we go. It couldn't work out the possibilities. We failed. So it turns out, while you could possibly program a computer to do everything, sometimes it's arguably more effort than it's worth. I hope that was interesting. That's the end of this. Thanks.